Welcome to the Data Encoding Seminar. This is Sarah and Ahmed. We're presenting today the Terradome.
Traditional methods for predicting sound acoustics in domes require a lot of manual calculations and simulations, which are time-consuming and it requires a lot of process. So the idea is to create an ML model which helps us to calculate these complex acoustic properties much faster. This model can help us predict the sound quality of different typologies of domes. Architects and engineers can use these predictions to enhance sound experience within these domes. First, we have the geometry generation from which we create the datasets. With those created datasets, we try to visualize and analyze them. With the analyzed data, we try different machine learning models, and then we do the prediction next. We have a sample of 1,000 domes to extract two different set of features. Dataset 1 has radius, heights, and volume. Dataset 2 has cross-section points and volume. We then simulate using Terradome to collect the values of sound pressure level and reverberation time. And we train them using linear regression and XGBoost, and then we do the prediction with these values. Sounds good? So now we look into the geometry generation. And next, to generate the domes using Grasshopper, we have inputted multiple circles with different heights. By running them in Terradome, we get the outputs of the sound pressure levels and the reverberation times. So this is the geometry generation where we have like multiple circles which are placed at different heights. And this is how the geometries for different typology of domes is being generated in Grasshopper. Now let's look into dataset generation. So we have like independent values for the domes and then dependent values which we acquire from Terradome. And dependent values for option 1, we have radius, height, and volume. And for option 2, we have cross-section point and volume. The highlighted ones are consistent, so we are dropping them from the dataset. This is the final dataset that we have collected for the domes. And so in order to get the dependent values from Terradome, we have like a sender and a receiver inside a fake room and a dome on the top. These are dependent values we got from the Terradome for 8 frequencies of SPL and reverberation time.
Then we started to visualize and analyze the dataset we collected. By plotting the 8 frequencies in relation to the geometry feature, we concluded that the SPL7 and RB7 has the most variance to the geometry. By that, we dropped all the other frequencies. Starting by plotting the option features on the histogram, we note that the radius option has a good variation to the data, while option points, specifically in the 0.3x, collecting only the data in a very small range, which can give us a bad prediction. Starting to looking for the PCA, for the option 1, we use the SPL means and RB means as a bin for visualization. You can see here a negative correlation with the volume in both SPL and RB, while in the RB it looks a bit noisy. For the option radius, we need a 4 PCA to run this model, while the R1 is have the most dominant feature. Correlation matrix score, all the features have a correlation related to each other. Moving to option 2, more or less all the features have a negative correlation with SPL and RB, except for the point X, while the RB looks very noisy, which gives us a hint that the prediction of the RB may not give us a good result. We need a 6 PCA to run this model, while the length of PT3 is scoring the lowest. So we decide for the PT3, here we have no correlation, so we decided to try it. Now we start training. As a recap, we want to predict the SPL7 and the RB7 separately, using regression model. To get the best results, we are training on the same set of domes, just representing the dome features in 2 different ways. Option 1, radius, height, and volume. Option 2, cross-section and volume. We're starting with the SPL. Using linear regression model, point option scored a bit higher than the radius, with a score of 0.95, 0.15 for the mean error, and 0.66 for the maximum error. Going next for the second model, which is the XGP, both showing a better scoring than the linear, with the point option still a bit higher than the radius, with a score of 0.994, mean error 0.05, maximum error 0.18. Here you can see the difference between the linear prediction and the XGP prediction. Now for the RB, starting with the linear model, both options are underfitting. both scoring less than 0.5, with the option 1 slightly better. Testing the XGB, the slightly better results with the less underfitting. Option radius score 0.54, with the mean error 0.03 and maximum error 0.12. After not getting a good results, we decided to train the model on a polynomial model. Still lots of noise, as we expected from very beginning. The training of the radius on the 4-degree scores 0.60, and for the points on 2-degree, we score 0.65 with a mean error 0.08 and maximum error 0.02. As a conclusion, for the SPL training, option 2, points and the cross-section, is better, while scoring higher in the XGP. For RB, all the results are not satisfying, scoring higher in the cross-section and points with 0.65, guessing that the RB need different dome features. Next, we're visualizing the prediction. Taking the SPL XGP prediction, comparing between both original SPL and the predicted one. Here we are plotting all the geometry features in a parallel graph with the SPL, and for the second one, for the SPL XGP prediction. Both performance SPL and SPL XGP prediction showing the same interaction with the geometry. Having to note that while having a lower PT3Z, PT4X and Z, and PT5X and lower volume, having higher SPL, which is still negative correlation. Thank you for listening.